Okay, so we're going to be looking at the Castigliano's theorem here. Basically what it tells us is the displacement, which is shown by this equation here, right there, and rotation, which is shown by this equation here. So first we're going to look at an example here, this one right there. Basically there's a point load applied here at point A and it's fixed on this end. It's just a simple cantilever beam. So the question's asking us to determine vertical deflection and rotation at point A. So here's the solution. First we're going to draw the free body diagram. And then first thing you want to do is we're going to find the moment equation as a function of x. So that's moment equals negative p times x. It's like that. So it'll be negative. Then we're going to find the partial derivative of this. So we can plug it into here. So it's just negative x because it's with respect to p. And then we're going to first find the deflection. So we're going to use this equation here, right there. And we're only looking at deflection due to bending, so we're just going to use this. So first we're going to plug it in there. And this equation goes over the entire length. So it's going to be from 0 to L, m, which is shown right here, times partial derivative of m with respect to p dx. And then we're just going to plug this and this into here. So this is equal to 1 over EI, 0 to L, negative px, times negative x, which is equal to 1 over EI, 0 to L, px squared dx. So now we're just going to integrate this, and as you can see this is a pretty easy integration. So this is equal to, you can take p out of the integral, so that's equal to p over EI times x over 3 from 0 to L, which is just equal to p over EI times L cubed over 3. So our deflection at point A is just equal to PL cubed over 3EI. And this is downward because we assume negative here. So we got a positive. So then it just ends up, the deflection's going down. And you can kind of see from this diagram here that it makes sense because the beam just bends down. Okay, now we're going to do the rotation at A. So basically, I'm going to use the same thing, and you use this. You're going to use this formula here, rotation. So basically, we're looking for this rotation at A with this point load, and that's A. And this length is L, and it's going to be a function of x. So basically we're applying this moment C here just so we can determine the new equation for rotation. So the new equation is going to look like the same as this one, negative px, except we're going to add minus c because of this counterclockwise rotation at c. It's just kind of like a virtual force. And then the partial derivative with respect to p would just be -1. And then we're going to plug this back into this rotation equation and just use this because we're just looking at rotation due to bending. So rotation at A is equal to 1 over EI, 0 to L, M times dm over dc. Actually, I made a mistake right here. This should be with respect to c is equal to -1, because from this equation you can see the partial derivatives with respect to c. So it's -1, as you can see from here. The derivative is just -1 of that. So then rotation at A is equal to this dx. Then we're just going to plug this and this into the equation. 0 to L negative px minus c times -1 dx. And this, so that just becomes positive px plus c. So that's equal to 1 over EI, 0 to L, px plus c dx. And because this moment here is just 0, then we can just get rid of that. So this ends up becoming 1 over EI, 0 to L times px dx. And then this is a pretty easy integration. So this just becomes p over EI times x squared over 2 from 0 to L. And plugging those in, those boundary limits in, we just get rotation at A is equal to p over EI times L squared over 2 is equal to PL squared over 2EI. And this is counterclockwise because it's assumed, we assume the rotation here to be counterclockwise and it's positive, so that's correct. So this is our rotation at A. And basically that's all. That's a pretty basic example of the Castigliano's theorem. Just asking for, we're just using these equations here to find displacement and rotation. And it's just, for a beam like this, we're just looking at the bending. So we're just looking at this, M. But some more advanced problems would be if you have axial deformation, you'd use this. And if you had torque or torsion, you'd look at this. So this was just a pretty basic example just to kind of introduce you to some of the formulas in the Castigliano's theorem. Thanks.